Today we're going to be looking at the gas laws, and before we start talking about the gas laws, I'd like to go over the variables that we're going to be considering when thinking about how our gases are going to behave. So there are 4 variables that help us predict how our gases are going to behave. The first one is pressure, and remember that's collisions with the sides of a container or collisions with anything that gas is hitting. The next variable we're going to be looking at is volume, so how much space that gas is occupying. Temperature can tell us or help us predict how our gases are going to behave. And the last one is moles, which is a quantity, how much of our gas we are looking at. And so for moles, the variable that is used is N. So lowercase n in the chemistry community represents moles, or how much, or the quantity of that gas. So those are the variables we're going to be looking at: pressure, volume, temperature, and moles. So our first law that we're going to go over is Boyle's law. Boyle's law is looking at the relationship between pressure and volume. So in this particular scenario, let's imagine 2 balloons. And in those 2 balloons, we have the same amount of gas, and those gases are at the same temperature, because we only want to be looking at pressure and volume. And let's say in this scenario that it's a balloon, it's filled with the same amount of gas, and one balloon is just kind of floating freely, and the other balloon is being squeezed. And so we can imagine that the balloon that's being squeezed has a smaller volume. Because it's being squeezed, those gases can't take up as much space. And so what we can imagine happening in the inside is if the balloon that is floating freely has more space or a greater volume, these particles on the inside are less likely to collide with each other and with the sides of the balloon. Whereas the balloon being squeezed has less space on the inside. So the particles that exist in here are closer together, meaning that they are more likely to collide. And more likely to collide with the sides of the balloon, meaning the balloon being squeezed, the gas on the inside has a greater pressure. So when we're looking at that, and I'll just use arrows, what we see is that as volume is increasing, then the pressure that gas is experiencing is decreasing. And vice versa is true. As the volume decreases, the amount of space those gas particles are allowed to occupy, then the pressure is increasing. Okay, so when we're looking at that relationship where as volume goes up, pressure goes down, and volume goes down and pressure goes up, there's a mathematical way to represent that. And so the formula for Boyle's law shows that. And so the formula is P1V1 is equal to P2V2. And what I always like to do is sort of show a very simple mathematical example of this. So if I'm looking at a simple example, let's say that we're looking at this instance over here where our volume was high and our pressure was low. So when the pressure is, let's say, at 1 atmosphere, we'll pretend that it occupies, and this is just for the sake of easy math, 10 liters of space. Well, that means that if I decrease the amount of volume or increase the pressure, let's stay with volume. So let's say I decrease the volume, and now I squish my balloon, and now it's only allowed to occupy 5 liters of space. What happens to this number? Well, this side is equal to 10, and this side so far is 5 liters. So pressure here must be at what? 2? So that this side will also equal 10. So to make the right side equal 10, then my new pressure must be 2. And that pressure is higher than the pressure on the other side, which is what I would have predicted. So as volume decreased, the pressure increased. And so when we're talking about that mathematically, that's referred to as an inverse relationship. Right? As one variable goes up, the other variable does the opposite and it goes down. When we're looking at Boyle's law, we're making two assumptions, that we have two constants. In this case, we're saying that moles are constant and temperature are constant, because both moles and temperature would also affect volume. So we want to look at just what pressure and volume's relationship is, while assuming that the other two aren't changing. So balloons that are tied, closed, and tight, and that are in the same room. All right, so that's our first law, and that's sort of how they're all going to go. Our next law we're going to look at is Charles's law. Now, in Charles's law, we're looking at the relationship between volume and temperature. So we're going to say that we still have two balloons, and we're going to say that they have the same amount of gas on the inside. And we're going to say that they're under the same amount of pressure. So they're both under atmospheric pressure in our pretend example. But in this case, one of them is in a cold environment and one of them is in a hot environment. And you have already seen this happen. The one in the cold environment sort of looked like it started to shrivel up and get a little bit smaller. Whereas the one in the hot environment, and had it been hotter, looked like it expanded. And so when we look at that, we can start to see what the relationship is. As our temperature decreases, like in this first scenario over to the left, then what we also see is that the amount of space that gas is taking up is also decreasing. So as temperature decreases, volume is also decreasing. And on the other hand, when we see temperature increase, we also see that the amount of space that our particles are taking up, our gas particles are taking up, is also increasing. So as temperature goes up, volume is going up. Mathematically, in order to represent this relationship, there is an equation for it, and it is V1 over T1 is equal to V2 over T2. And again, I like to show just a quick mathematical representation of this. So again, let's look at our two examples, our two balloons, and we'll use really easy numbers just to make it very clear and visible. So let's say that our initial volume was 2 liters, and it was at a temperature of, let's say, 100 Kelvin. Then, as you heat it up, let's say to 200 Kelvin, in order to get this side and this side to be equal, then our new volume has to be, in this case, 4 liters. So we see that as temperature went up, so did the volume. So that equation is our mathematical interpretation of that relationship. What things are staying constant in this case? Well, in order to look at just volume and temperature, then pressure and moles of gas must be staying constant. So we're assuming those things aren't changing, so we can see just the relationship between volume and temperature. Now, because in this case, as temperature goes up and volume goes up, as temperature goes down, volume goes down, the relationship is direct in this case. So as one goes in a particular direction, the other one goes in the same direction. All right, so our next law is Gay-Lussac's. You'll have to make that little correction in the notes. And in Gay-Lussac's law, we're looking at the relationship between pressure and temperature. So in this case, instead of being in balloons, because balloons have a flexible volume, they can be larger or smaller, we're going to be in closed, rigid containers. And when you're in a closed, rigid container, your assumption here is that volume is not changing. We are Also assuming that because it is a closed rigid container, that our moles of gas are also not changing. Right, so gas can't get in or escape because they are closed containers. So now what we're going to do is we're going to change the temperature. And so if you can imagine you have like a can of something, a can of gas, I guess, and you cool it off, we would predict that these particles would slow down. And if they slow down, they're going to collide less. And if you were to heat up that same rigid container or a different rigid container, we would expect that our particles would speed up and that they would collide more. So in this case, as our temperature increases, we also see that our pressure is also increasing. And then when our temperature was decreasing, in our example, our pressure or our number of collisions was also decreasing. So again, temperature goes up, pressure goes up, temperature goes down. We expect the pressure to go down. And in order to show this in a mathematical expression, we use the formula P1 over T1 is equal to P2 over T2. So it's very similar to the equation above, except for in this case, instead of volume and temperature, we're looking at pressure and temperature. In this case, we made two assumptions that two things were constant. The first one was volume. Again, they were in rigid containers, so there's no ability to expand or shrink. And the second one was the amount of gas, or the moles of gas was constant. So nobody was putting extra moles into any of the cans. We're just looking at how fast or slow our particles are moving. In this case, again, because temperature is going up, pressure is also going up, this is considered a direct relationship. All right, our next law is combined gas law. It is literally just a combination of the laws that are above. So in this case, it is a combination of the three laws that we just saw. So Boyle's, Charles, and Gay-Lussac's. So if you look at those equations and you combine them all into one, we see that temperature will definitely be on the bottom because it is on the bottom for both Charles and Gay-Lussac's. And then pressure and volume will both be on the top, and the equation will look a little bit like this. In this case, the only variable that is still constant is moles of gas, or the amount of gas that we have. In this case, because pressure and temperature have a direct relationship and volume and temperature have a direct relationship, but pressure and volume have an inverse relationship, you can't answer what the relationship is because it's sort of a mix between the two. So you'd really have to see what are the numbers for pressure, what are the numbers for volume, and what are the numbers for temperature to see how any changes might affect your gas. All right, our last law that we're going to talk about in this set of notes is Avogadro's law. And Avogadro's law is looking at the relationship between moles of gas and volume of gas. So in this case, we are going to assume that we are under atmospheric pressure. So we have the same pressure and that we're just at regular room temperature. So we're at the same temperature. So both of these balloon bag things are at the same pressure and same temperature. So you can imagine that when you are blowing into a bag or into a balloon, that you're increasing the number of actual gas particles that are inside of here because you're blowing gas into it. And as you blow gas into a flexible container like this bag or like a balloon, then your volume is also going to increase. The size of the balloon will get bigger. If you were to release that bag or balloon and you were allowing the air particles to leave, the gas particles to leave, then we're going to get a reduction in our moles of gas, and that's going to cause a reduction in volume. So the size of our balloon or our flexible container will get smaller when there's less gas inside. Again, there is a mathematical way to represent this relationship between volume and moles, and it is most normally recorded as V1 over N1 is equal to V2 over N2. So really quickly, mathematically, just to show you how that is showing this relationship as one increases, the other increases, as one decreases, the other decreases. I'll just use some easy numbers here. So let's pretend that the volume is at 10 liters and that our moles of gas is 1. So we have 1 mole of gas. And let's say that I go ahead and I decrease the size of my balloon. Well, in order for this side and this side to be equal, well then this number is also going to have to be smaller. So if volume decreases, moles decreases. If volume increases, moles increase. We'll have lots of practice with this, so you'll see lots of example problems. In this case, we said that 2 things have to stay constant. The first one was pressure. So they have to be under the same pressure to see this relationship. And the other one was temperature. If volume goes up and moles goes up, then this is going to be showing a direct relationship. All right, so that was our last gas law for this set of notes. I'll do a separate video for ideal gas law.